In this video in section 13.2, we're going to get into some more examples looking at level curves of various functions. So here we have problem number 4, where we're asked to graph several level curves of the following functions. And so starting with part A, right, we have f of x, y is 5 times e to the negative quantity x squared plus y squared. So looking at the level curves, okay, again, we're looking at setting our function f of x, y equal to a constant, right? We're asking what are all points on our surface that are at various fixed altitudes, right? So this would translate for this particular function to 5 times e to the minus quantity x squared plus y squared, and that's got to equal c. Okay, so now this is fairly unfamiliar looking, so I'm going to go ahead and get rid of the exponentiation. Okay, so I'll first go ahead and just divide by 5. So I'm looking at c over 5 on the right hand side, and then I'm going to go ahead and just take the log of both sides, so that's minus the quantity x squared plus y squared would equal the log of c over 5. Okay, and then finally I'm just going to move that negative over, and so I'm looking at x squared plus y squared is equal to minus the natural log of c over 5, right? Now, although this still looks a little intense, this really is what? Just a circle. It's x squared plus y squared is equal to the square root of minus the natural log of c over 5 quantity squared. Okay, so we're seeing here that again this is a circle of radius r is equal to minus the natural log of c over 5. Okay, so although this expression is fairly complicated for the radius, right, the bottom line is that we're just going to get a whole bunch of circles centered at the origin for our level curves. Okay, so one comment here before we go to graph these things. In order for this expression here for our circle to give us something real valued, right, we need the thing inside that square root to be non-negative, right? So we need, in other words, this thing to be non-negative. Now, what exactly does that imply about c? Well, notice if I multiply both sides by -1, that's saying that the log of c over 5 would be less than or equal to 0. And now exponentiating both sides would say that c over 5 is less than or equal to e to the 0, which is just 1. And then moving the 5 over is telling us that c is less than or equal to 5. So that's telling us, right, that our surface has a maximum altitude here of 5, right? In other words, our surface lives below the plane z equals 5. We are going to touch z as 5, as we'll see here in a moment, but anyways, let's keep this in mind. So now let's go ahead and look at the graphs. Okay, so I've gone ahead and just plotted a bunch of these circles by plugging in some different values for c. So for example, if c is 5, notice here you're going to get the natural log of 5 over 5, or in other words, the natural log of 1. Now that's 0. So here we're going to get that scenario where we can think of the circle as a circle of radius 0. So in other words, we're just going to get the origin there when c is 5. Okay, and then as we know, c can't exceed 5. So if I put in like c is 4 or c is 3, so on and so forth, I'm going to just get these concentric circles. Okay, now they look kind of evenly spaced here. They're not actually evenly spaced. As you might suspect from this complicated looking expression for the radius. Okay, but now with this in mind, let's go ahead and look at the graph here. I have my surface. Here, I'll get rid of this for the moment. Here's my surface. We looked at this before, just a nice mound-shaped, symmetric-looking thing. And so now what we're doing to find the level curves, right, is you can think of just intersecting our surface with this plane as z equals c, right? And as we let the height vary, right, so we're just cutting out all these cross sections, right? This is a nice view of what those cross sections are going to look like. We're just getting a whole bunch of concentric circles. Okay, so that agrees with what our answer is. And notice also, of course, when z is 5, we are right there at the peak, right, of our little mound. Okay. Okay, cool. So now let's go back, and with that, we'll move on to part B. Okay, so for part B, we're looking at g of xy is 1 minus y squared. So again, for the level curves, we will just set g to a constant. And here we're saying, well, I'm going to get 1 minus y squared is equal to c. And now if I do a little rearranging here, I'm going to get y is equal to, now when I take square roots, I'm going to get a plus or minus the square root of 1 minus c. Okay? So thing to keep in mind here is that c is constant, right? So what we're saying is that y is equal to some positive constant and some negative constant. And if you set y to a constant, you're going to get a horizontal line. So these right here are really, and you can kind of, because I'm going to get a positive and a negative value, you can say we're really getting a pair of horizontal lines. Okay. All right. So as an example here, like let's say, c is equal to 0. Okay, then we would be getting the lines y is equal to plus or minus 1, right? So that's just two horizontal lines. So more generally, here's some illustration of what various level curves are going to look like. So if you set say c equal to 1, right? That's special in the sense that that will make this thing 0. And so if y is 0, that's just going to give you the x-axis. But now if you let c be something like, I don't know, say 0, like we did here, see we're getting these pairs now of horizontal lines. C is a half. We would get this plus or minus the square root of 1/2, so on and so forth. Okay, and also one quick note as well. This condition is saying what? That c has to be less than or equal to 1 for this thing to be real valued. Okay, so keep that in mind. Let's go to the graph like we did for the last example. Here, I'm going to take this plane out and that other surface. What are we looking at? Well, here, notice if I just look in here's the y-axis and here's the z-axis, I'm just seeing, right, this parabola, z is equal to 1 minus y squared, right? Just upside down parabola shifted up 1. But now notice, since this equation is independent of x, we're just going to get a whole bunch of parallel copies of that parabola as we run along the x-axis, right? So this is what we could call a parabolic cylinder, right? We're just basically taking this plane curve, which is the parabola, and then just basically copying it in a parallel fashion. Cool. So now when we go ahead and start intersecting this thing, notice, okay, as z is equal to 1, there's 1, we're right there at the top of our surface, okay? And that's why we're seeing just that one line of intersection, which is along the x-axis. And now as I start to go in, right, for points or for intersections like this, see, we're going to get a line over here and a line over here. They're going to come in pairs. Okay, and one other thing to notice here is the spacing. Okay, as you let C, in other words, the altitude, get more and more negative, these pairs of lines, the successive pairs, will get closer and closer to one another. Okay, and that's consistent with this parabolic shape here for our surface, right? So, you know, the spacing up here would be greater than the spacing you're going to get down here for these successive pairs. Okay, so that is that one. So let's go ahead and check out next part C. So for C we got 5 minus x minus y. So again, for the level curves, we'll just set h equal to a constant. And here, what we're going to get is 5 minus x minus y is equal to c, and rearranging here, we see that, hey, these are what? These are nothing other than a bunch of lines in the plane. Okay, so these are going to be a bunch of parallel lines. Okay, and just to illustrate here, so for example, if I set c to 0, I'd get x plus y is 5. So I see the intercepts are at 0, 5, and 5, 0. C is 1. You'd get x plus y is 4, right? Very similar thing there, so on and so forth. Okay, so now one comment on this one, right? What kind of a function is this? This thing is just a linear function. And as we saw in a previous video, right, linear functions of two variables just describe planes in three-dimensional space. Okay, so now with this in mind, let's go ahead and check out its graph. Okay, well, I'm going to just take this blue plane now, and I'm going to intersect it with a bunch of planes, right? And these things are just going to intersect in lines. And so, and of course, they're going to be parallel lines, right? As we can see as I slide this orange altitude plane up, right? I'm just going to be tracing out a bunch of these parallel lines, okay? So yeah, that makes a lot of sense, okay? And then pressing on to the last one, this is D. So for here, we got the root of x squared plus y squared. So for our level curves, okay, we'll set f of x, y equals a constant. And now we're going to get the root of x squared plus y squared is c. And now squaring both sides, we get x squared plus y squared is equal to c squared. Okay? And these, of course, are just circles of radius c. So circles of radius c. Okay, so if I look at those, I'm going to get a picture like this, right? If c is 0, right, well, I'm just going to get the origin. If c is 1, you get the unit circle. If c is 2, you'll get the circle of radius 2. If c is 3, right, circle of radius 3, so on and so forth. So here, notice since it's the radius is c itself as opposed to the square root of c, like we saw with the paraboloid, okay, these contours are all going to be evenly spaced. So that kind of suggests that this thing is a cone. And in fact, that is the case. So here I'll go ahead and plot the cone. Okay, and so here's our nice surface. Okay, nice and symmetric, and I'm going to go ahead and intersect that thing, and yeah, I'm just going to get these evenly spaced circles, right, centered at the origin. Okay, so that makes a lot of sense. All right, great. Well, that is going to do it for this video. I'll see you next time.